Okay. So at this, part of the lesson, we will discuss um how do we evaluate trigonometric and hyperbolic function whose arguments or whose inputs are complex numbers. Okay. So as we all know, if you have a function, okay, if you have a function, say f of x, okay, and this applies to any function, okay, whether this function is um, a polynomial function or a transcendental function, such as trigonometric, hyperbolic, and logarithmic functions, or if this is an exponential function. We all know that if the input or if the argument of this to this function is a complex number, okay, this also the result, the value of the function is also complex valued. Okay, so that is why in this part of the lesson we need to learn how to evaluate functions, okay, that are transcendental in nature. Okay, so when you say transcendental function, these are non-algebraic functions. Okay, like examples of transcendental functions are include trigonometric functions, hyperbolic functions, logarithmic functions. Okay, so um, but the basis of how we can use this or how we can evaluate these transcendental functions whose input are complex valued. Okay, um, is based on the fact that we can actually use the Euler formulas here. Okay, as we discussed them in the previous section. Okay, so so we recall that the Euler formula has this one. Okay, and is this also for the conjugate? Okay, so remember that e raised to ix and e raised to negative ix are conjugates of each other. Okay, and so therefore, and so they're polar forms. They're also conjugates. So ito and this one are conjugates. Okay. Now, what we can do here is that we can have the first equation e raised to ix, okay, equals cosine of x plus I sine of x, okay, and then the conjugate or its conjugate e raised to negative ix, okay, equals cosine of x minus I sine of x. Okay. Now, if we add these two equations, okay, if we add these two equations, on the left side, the sum would be e raised to ix, okay, plus e raised to negative ix. Now, on the right side of the equation, the sum would be simply 2 cosine of x because this term and this term cancel results to 0. The sum of these two terms is 0. So therefore, what is retained here is 2 cosine of x. And then we solve this for cosine of x. We will have 1/2 times e raised to ix, okay, plus e raised to negative ix, okay, which is what is depicted here. Okay. Now, in the same manner, you start from these two equations. Okay, you start from these two equations, and then instead of adding them, you subtract them. Okay. And then what will be retained is the function sine of x, which will give you which when we solve for sine of x will give you this formula. Okay. Now, this assumes that x is a real valued number. Okay. So in this case, x is real valued. Okay. But as we did with the exponential function, okay, e raised to x, okay, we actually extended this by assuming that your exponential function can actually take an exponent that is complex. Okay, we can also do that same technique here. That is, if we assume that x here, okay, would actually take a complex number as its value or as its argument, then we can just simply replace x with z. But remember that z now is complex valued. Okay, and then we will have the following definitions. Okay, so cosine of z is 1/2 of e raised to iz plus e raised to negative iz, and then sine of z, okay, equals 1/2i okay, times e raised to ij minus e raised to negative ij. Okay. Now, this now establishes the relationship, okay, between um, trigonometric functions and exponential functions. Okay. So, in the realm of real numbers, we simply don't have the means to connect exponential functions and trigonometric functions. They are completely unrelated. But that is only in the case of real numbers. Okay? In the complex domain, however, okay, the two unrelated functions are actually related, okay, to each other. Okay, so um, this is not something that is surprising when it comes to the relationships between different functions when these functions assume complex valued arguments. Okay. We can later on we will relate the hyperbolic functions also to exponential functions and to trigonometric functions. Okay. Via the complex numbers. Okay. So here's the thing. In the real number domain, okay. Your hyperbolic functions are related to exponential functions. Okay, they are related to exponential functions. For example, the definition of hyperbolic cosine of x, okay, is equal to e raised to x plus e raised to negative x over 2. So these two are related. But these two, the hyperbolic and the exponential functions, are nowhere to be related to the trigonometric functions. They simply don't have the relationship. These two functions don't have that relationship to trigonometric functions. Okay. In fact, hyperbolic functions are basically exponential functions, but has analogs with the properties of trigonometric functions. Okay. Merong mga properties na pinopossess yung hyperbolic functions that are the same or that are identical to the trigonometric functions. Okay? But basically, ang hyperbolic functions are not functions of angles. Okay? They don't work on angles. Okay? The argument here is not actually an angle measurement. Okay. Remember the trigonometric functions, yung mga trigonometric functions natin. Okay. For example, when you say you have sine of x, okay, you have sine of x, it is understood that this x is actually an angle measurement. Okay. This is an angle measurement. Okay. But in hyperbolic function, this number is not an angle measurement. Okay. It may be a measurement of length. Okay, it may be a measurement of mass. Okay, but it's not necessarily just an angle. Okay, so the hyperbolic function and the trigonometric functions are completely different functions. They are unrelated. Okay, they are completely unrelated functions. But the properties of hyperbolic function closely resemble that of the trigonometric function. Okay, they very closely resemble. They are very identical to or most of them are the identities to be established in hyperbolic functions. Okay, are very close to what the trigonometric function exhibits, or the identities of the trigonometric functions exhibit. Okay. And that is in terms of real number. But when you when you consider these functions into in the complex number domain, okay, if you consider these three functions in the complex number domain, okay, there is a bridge now that would connect the sine function to the exponential function, and later on to the hyperbolic function. But that only happens when they take complex numbers as arguments. Okay, when x here and x here are complex numbers. Okay, so these two will be related to each other. Okay, and we will try to establish those properties. Okay, that connects the two when it comes to the complex number domain. Okay. Um, so here again, at this point we consider z to be um, is complex value, and even then, okay, even then, the trigonometric functions, okay, retain their definition. Okay. Um, now, when we say the function is entire, there is a statement here that says since e of z is entire, it means e of z, e of z is entire. Okay, it means okay that the function e of z is defined, okay, and non-zero for all z. Okay, so no matter what value your z assumes, okay, there is always a non-zero value for e raised to z. Okay, in fact, you can just simply take a look at e raised to x, okay, which is where x is a real number. Okay, and this and realize that this e raised to x actually never becomes zero, no matter how small x is. E raised to x is never zero. Okay? Kahit sabihin yung e raised to negative 18 pa yan, that number is very close to zero, but that is not necessarily zero. Okay? So we say that e raised to x is entire. Okay? And thus, it also would follow that the complex extension of the exponential function is also an entire function. Okay? But the thing is, based on these properties, okay, based on these properties, since e raised to z, this and this are entire functions, that also makes cosine of z and sine of z also entire functions. So they are defined for all values of z. Okay, but that's not the case for tangent and tangent of z and secant of z. Okay, because cosine of z may be zero at some point. There is a value for there is a value of z that would make cosine of z equal to zero, and in that case, your tangent of z is not defined. Okay. In the same manner, cotangent of z and cosecant of z is not entire because it is possible that your sine of z can be zero. Okay. So in that case, your cotangent of say and cosecant of say becomes infinite. Okay. Um, and so at those points, those functions are not defined. Okay. So the real and imaginary parts of cosine of say and sine of say are needed in computing values, and they also help in displaying the properties of our function. So basically, what we will attempt to do is to have cosine of say, or to evaluate cosine of say, okay, when j is equal to x plus iy, okay, and see what would the value come up to, okay. That is why we say that we need to compute the real and imaginary parts, okay, because cosine of say, okay, would result to another complex number, okay, say that would be p plus iq. Okay, here since p plus iq is a complex number, both p and I and q are real numbers. Kaya lang nagiging complex nga siya dahil yung q, the imaginary part, okay, or the imaginary component, we multiply it by the imaginary unit. So that is why it becomes a complex number. So what we will attempt here is to evaluate basically what is cosine of x plus iy. Okay? So, that is covered actually in example 8. Okay, so let's try to prove the following identities. Okay, so let's start with cosine of j. Okay, so let us prove that cosine of z equals cosine of x hyperbolic cosine of y minus I sine of x hyperbolic sine of y. Okay, so we start with um, letting z equals x plus iy, and so we will have cosine of x plus iy, which when we use the sum of angles identity for cosine. Okay, this would be, or this will translate to, or this would be written as so you might want to review this trigonometric identities for sum and differences of angles. So what we need is this one. Okay, is the third identity. So cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Okay, so using that identity, we can actually write this as um, cosine of x, okay, times cosine of iy, okay, minus minus I sine of x sine of iy. Okay, so now at this point we need to do something about cosine of iy and sine of iy, because basically cosine of x is okay by itself because you will be able to evaluate this since x is a real number, but iy is not a real number, so you don't have as of at this point we cannot evaluate your cosine of iy directly. But let's try to establish some relationships. Okay, so recall that cosine in the previous formula, okay, we have cosine of z equals 1/2 um, e raised to ij plus e raised to negative ij. Okay, so we were able to derive that one. Now, at this point, let us let z to be iy. So we will replace z here, okay, with iy, so that we will have cosine of iy, okay, equals 1/2 times e raised to I times iy. Okay, so that's again, it's e raised to I times iy, okay, plus e raised to negative I times iy. Okay. Now, take a good look at the exponent. So this is I times iy. Okay? And I times I is I squared, which is basically negative 1. Okay? So this entire product, say I times iy, becomes negative y. Okay? So rewriting that one, we will have 1/2 times e raised to negative y plus e raised to negative I times iy is positive y. Okay, that becomes I times iy, so that is negative I square times y, and I square is negative 1, then multiplied by negative 1, that becomes positive y. Okay, so this exponent becomes positive y. Okay, now rewriting this, because this is simply this is simply an addition, so I can actually interchange them. So I can rewrite this as e raised to y plus e raised to negative y. Okay, which basically is a formula that you should be familiar with as the hyperbolic cosine of y. So this one. Okay. So notice that that one, okay, is this one. So that's e raised, instead of just using x, I used y here. Okay, so e raised to y plus e raised to negative y times 1/2 is hyperbolic cosine of y. So now, we were able to establish that um, we will be able to establish that cosine of iy is equal to hyperbolic cosine of y. Okay, this is something that I was telling earlier. Okay, I was proposing earlier. Okay, with complex numbers. Okay, with complex numbers, the two seemingly unrelated functions, such as a trigonometric function and a hyperbolic function, becomes related. Okay, in fact, we can convert a trigonometric function, okay, to a hyperbolic function if only that the argument for the cosine function or for the trigonometric function is a purely imaginary number, such as iy. Okay? So we see that cosine of iy converts to hyperbolic cosine of y, which is now a real number. Because y is a real number. Okay? Y is a real number. Then hyperbolic cosine of y is also a real number. Okay? Which is something that we can now evaluate. Okay? And that is our goal here. Actually, our goal here is to actually make this enable us to evaluate this one. Okay? And since we established already that cosine of iy, which is which cannot be evaluated because the argument of cosine is a complex number. Okay? But we have established that this one is equal to hyperbolic cosine of y, which is a real number. Then we can evaluate now this side. If we replace this cosine of iy as hyperbolic cosine of y. Okay? Now we can do the same thing with sine of iy. Okay? Again, we will start with sine of z as established in the previous formula. This one. So established here. Okay, so we have here um 1 over 2i times e raised to ij minus e raised to negative ij. Then again, we will have to let z equals iy. Okay? So we will have now sine of iy equals 1 over 2i times so this becomes the exponent here becomes I times iy, which should give you negative y, as we have established earlier. So this becomes e raised to negative y as we substitute iy to z here. Okay? And then the other side becomes e raised to y. Okay? Now, the next thing that we will have to do, okay, because as you might have predicted, we would try to convert this to to hyperbolic sine of y. Okay, we will try to or we will attempt to have sine of iy equal to or related to hyperbolic sine of y. Okay, but in this case, you do have a problem with this one. Okay, because they the terms are interchanged. Okay, because in hyperbolic sine of y, what the term e raised to y comes first. Okay, as a minuend. Okay, as the first term, or as where you would subtract from e raised to negative y. Okay, and you see that they are actually in reverse there. Okay, but let us take a look, or let us take a good look at what at what I 1 over I is actually equal to. Okay? So let us establish the identity for 1 over I. Okay? And to be able to do that, we need to rationalize this one. So I'll multiply this with I over I. Okay? Again, I divided by I is simply 1. Okay? So this now gives you I over I squared. And again, what is I squared? I squared is negative 1. So therefore, this becomes negative I. So that means, okay, that means, um, 1 over I can be replaced by negative I. Okay? So here, the 1 over I here will be replaced by negative I. So that becomes negative 1 half times I times e raised to negative y minus e raised to y. And then what I would do is I would multiply negative 1 to the terms inside the parentheses. Okay? And that should become, okay, that should become 1 half I times e raised to y. This term now becomes positive and this becomes negative. So minus e raised to negative y. Okay? Which, when we actually first remove I, okay, and instead place it here, okay, wait, now there, clearly, this factor, this 1 half times e raised to y minus e raised to negative y is hyperbolic sine of y, okay? That is hyperbolic sine of y. So therefore, okay, as we have seen here, that since this is a hyperbolic sine of y, we can simply rewrite this as, or I'll write it here so that I can separate it from the rest of the writings. Okay, we will have sine of iy, okay, equals I, this I, and then the rest of the term is hyperbolic sine of y. Okay? And we can now evaluate what is hyperbolic sine of y because hyperbolic sine now takes a real number. Okay? Yun nga lang, the entire result of sine of iy is actually a purely imaginary number. Yung entire result nito okay, is that is what the imaginary number is. Okay? Dahil may nakamultiply na I sa kanya doon sa hyperbolic sine. But hyperbolic sine itself is a real number because y is a real number, and if you substitute a real number to a function, the output of the function or the result of the function is a real number. But nevertheless, we are able to establish two things. That hyperbolic cosine of iy of a purely imaginary number equals hyperbolic cosine of y. Did I say hyperbolic? The cosine of iy, okay, the cosine of an imaginary number is equal to the hyperbolic cosine of y. Okay, and sine of iy is I times the hyperbolic sine of y. So now we are now we are now able to establish the relationship between the trigonometric functions sine and cosine to the hyperbolic functions, hyperbolic sine and hyperbolic cosine respectively. Okay, now going back here. Okay, let's go back at this point. This one. Okay, so I'll write it down here. We see that we can simply replace cosine of iy, okay, with hyperbolic cosine of y, so that it becomes so that it would allow us to evaluate that number. Okay, and in the same manner, we can replace sine the factor sine of iy as I hyperbolic sine of y, so that we establish that cosine of z, where z is a complex number, equals cosine of x, okay, cosine of x times hyperbolic cosine of y, okay, minus I, this I comes from this one, okay, but I'll write trigonometric sine first, and then I'll multiply it with hyperbolic sine of y. Okay? So at this point, we are now able to establish the formula for cosine of z if z is a complex number. Okay, so take note, okay, that x is a real number, y is a real number, but x plus iy is not a real number because one of the terms, which is the I component, is multiplied by the imaginary unit. So this entire thing is a complex number. But still, remember that even if we use them as components for your complex number, both x and y are still real values or real numbers. So that is why if you actually substitute these real numbers to cosine function and to hyperbolic cosine function, we'll still have a real number as an answer. So this cosine of trigonometric cosine of x times hyperbolic cosine of y, their product is basically a real number. Okay? And that forms the real part of cosine of z. Okay? So this forms part, okay, of the real part of cosine of z. Okay? This part, okay, this product is the imaginary part of z. Okay? But take note, still, the product trigonometric sine x times hyperbolic sine y is a real number. The product is a real number because x is a real number, sine x is a real number, y is a real number, therefore hyperbolic sine y is a real number, and their product would still be a real number. Okay? So it means when I say that these functions are real numbers, it means that you can be able to calculate them. You can be able to evaluate them because there is simply no way that we can actually evaluate directly, okay, the values of functions having complex numbers as inputs, especially in the cases of transcendental functions such as trigonometric and hyperbolic functions. Okay? But making the values, okay, making these values real, like sine of x and hyperbolic sine of y, making them real, allows you to evaluate them at a particular value. Okay, so as long as we know what z is, so that is, say, for example, that's 3 plus 4i, okay, your cosine of 3 plus 4i should evaluate to cosine of 3 radians, okay, cosine of 3 radians times hyperbolic cosine of 4, and 4 here doesn't have a unit, not radians, not angle, because 4 here might be a unit of length, for example. Okay, so as I discussed earlier, that's the main difference, okay, between the trigonometric and hyperbolic functions. Hyperbolic functions are trigonometric functions take in angle measurements as their input, whereas hyperbolic functions can virtually take any kind of measurement. Okay, so you'll be able to evaluate this using your calculator. And the second part, or the second term, is minus I times sine of 3 radians times hyperbolic sine of 4 radians. Okay? So, again, we will be able to evaluate this using your calculator. We will be able to evaluate this using your calculator. And we will have the value of cosine of 3 plus 4i as being complex valued if you take all of this, okay, as your answer. So again, when you are inputting, when you input a complex value or a complex valued input to a function, generally, the value of the function also becomes complex. So in this case, that holds true. Okay, but it actually is not a, it's not a guarantee, okay, that your function, okay, would be complex if the input is complex. Okay, pwede rin namang purely imaginary maging output niya, or in some cases it can be purely real. Okay, but one thing's for sure, there is a high probability that if the input of a function is complex, the output or the outcome of that function, or the value of that function, or the resulting value of that function is also complex value. Okay? Now, what I want you to do as an exercise is to actually work on letter B. Okay? So if you are able to to study this way or this manner by which I did establish um this formula, okay? So we were able to establish this, okay, in the previous example. What I want you to do now is to actually try to establish um equation 6 letter B. That is, how do you evaluate sine of x plus um, iy. Okay. Now let's also proceed with verifying the following identities. Okay. So this is for 6a, and then 6b is for your exercise. Okay. And let us try 7a. Okay. So let us now try to establish the formula under 7a. Okay, which is the magnitude of, or the square of the magnitude of cosine of z equals cosine square x plus hyperbolic sine square y. Okay. Again, basically take note that say z is x plus iy. Okay, it's a complex number. But we really need not substitute this here, okay, and complicate matters. But let us start from the fact, okay. Let us start from the fact that taking note that the symbol cosine of z is actually the magnitude, okay, is the magnitude of um, cosine of z. Okay, take note that cosine of z itself is a complex number, and so you would be able to take its magnitude. Okay, say for example, since let us let w, okay, equals cosine of z, okay, which should lead us, for example, um, say that number is a plus bi. Again, if cosine of z is a complex number, it would take the rectangular form a plus bi. Okay. Now, if we attempt to find the magnitude of w, which is basically the magnitude of cosine of z. Okay. Basically, that's the magnitude of cosine of z. Okay. That should require us to compute the square root of a square plus b square. But because that's the magnitude of w. Okay. And so, we find that cosine of z, or the magnitude of, or the square, okay, of the magnitude of cosine of z is found by squaring this right side, which should give you a square plus b square. Okay? So, but in this case, what is a and what is b? A and b are actually established in this part. Okay? This is actually a. Okay? This is actually a. And this is b. Okay? So, we take note that in this case, your a is cosine x, hyperbolic cosine of y, okay, and b is sine x, hyperbolic sine of y. Okay? So therefore, the magnitude, or the square of the magnitude of cosine z is basically the square of this one. So that is cosine square x and hyperbolic cosine square y. Okay? Plus the square of b, which is hyperbolic trigonometric sine square x. Okay? Plus times hyperbolic sine square y. Okay? So that is what is this quantity equal to. Okay. Now, there is this identity. Okay, there is again, you have to review your trigonometric and hyperbolic function identities. Okay. But two of those Okay, one from the trigonometric side and one from the hyperbolic side that we will use in order for us to uh, manipulate this into the form given by 7a is number one. On the trigonometric side, we have cosine square x, okay, plus sine square x equals 1. Okay, I'm pretty sure that you know this one. Okay. And on the hyperbolic side, okay, we have the identity hyperbolic cosine square x minus hyperbolic sine square y square x equals 1. Okay? So, actually, this is the reason why, one of the reasons why, again, hyperbolic functions are made to look like trigo trigonometric functions, even though they are basically or fundamentally exponential functions, is that some of their properties and some of their identities are analogous or is similar to their trigonometric counterpart. So, for example, these two. Although there is a difference between the signs. Okay, so you have the difference between the sign between the terms. Okay, but um, in some there are other identities that are very similar. Okay, between the trigonometric and hyperbolic functions. But in this case, the Pythagorean identity. This is what we call in trigonometry. This identity is called the Pythagorean identity because it actually resembles the Pythagorean formula, which is a squared plus b squared equals c squared. Okay, so the analog of the Pythagorean formula or identity in the hyperbolic function side is this one. But instead, take note that this is minus or this is minus sign. Okay, you can actually establish this. Okay, you can actually establish this identity by using the definition of by using the definition of the hyperbolic functions. Okay, this one. Okay, so that is if you actually perform the operation hyperbolic cosine of x squared minus hyperbolic sine square x, okay, into this exponential expressions. Okay, so that is e raised to x plus e raised to negative x over 2 square minus e raised to x minus e raised to negative x over 2 square, and then try to compute the value of this. This actually becomes 1. Okay, so I leave that to you as an exercise. Okay, I leave this part on you as an exercise. Okay, so going back. Okay, going back in this case.